Okay, ladies and gentlemen, as you heard, my name is Stephan Lang. I'm working at the University of Stuttgart Institute for Building Energetics, Thermal Technology and Energy Storage. And I have now the honor to present to you my research done on ultra-high temperature thermal insulation for ultra-high temperature thermal energy storage. But before I talk on this, let me allow to quickly introduce my institute. I formerly worked at the ITW, which was the Institute for Thermodynamics and Thermal Engineering, which was then in July 2018 merged with the Institute for Building Energetics and Institute for Energy Storage into the Institute for Building Energetics, Thermal Technology and Energy Storage. We do work and research on solar technology, energy storage, testing and inspection for components, solar and energy efficient buildings, smart cities, energy efficiency and cooling technology. So if one of you is interested in services on one of these topics, please just contact me after that. Okay, now coming to the content of my presentation today. First, I'm going to show you the background and aim of my work, and then the motivation for a preferably high insulation performance, but also very high insulation efficiency. Then I'll show you the thermal insulation techniques I considered mainly, and then a market screening for ultra-high temperature thermal insulation materials. Then I'll show you a cost efficiency comparison of different thermal insulation techniques and some optimization potential for the efficiency of thermal insulations. So, beginning now with the background, aim, and motivation. The background of my work is the Amadeus project. You probably all remember the working principle of it. I just want to point your attention at one thing, and that is the temperature of up to 2000 degrees C. As at the beginning of the project, we considered temperatures for up to 2000 degrees C, as we also considered boron as part of the alloy, which melts at around 2000 degrees C. And that's why I also did research on thermal insulation materials up to this temperature. So what was now the aim of my research on thermal insulation? It was finding the most cost-efficient thermal insulation for a thermal energy store with temperatures up to 2000 degrees C. And to reach that aim, I followed the following 3 steps, which I mainly explained to you in the content slide. It's the screening for suitable commercially available thermal insulation materials for temperatures up to 2000 degrees C, and comparison of different insulation techniques and research on insulation optimization. So what is now the motivation for preferably high insulation performance? I think the first point is pretty obvious to everybody, is decreasing the energy losses. And when it comes to thermal energy stores, it's also increasing the storage time. And for some applications, it might be of advantage to have a preferably high temperature homogeneity of your process, as for example also for the Amadeus project, as for example Mirto told you in the last session. And okay, but why we not only want a high insulation performance, but also a very high efficient thermal insulation? And when we talk about porous thermal insulation materials, that means a low thermal conductivity. The main reason for this is that we want to keep the total volume of our device small, as the main advantage of our technology is actually a very high volume-related energy density. So if you put too much insulation material around, this would go in the other direction. And then you have to keep in mind that the heat losses are proportional to the surface of heat transfer to ambient. So what does that mean for the insulation? I show you this on that simple example. We have here a cube with an edge length of 1 meter and a temperature of 2000 degrees C, surrounded by a thermal insulation with a thermal conductivity of 0.1 watts per meter Kelvin, and surrounded by ambient air with a temperature of 30 degrees C. What happens now if we increase the insulation thickness is that we also increase the outer surface of our insulation, and thus the surface of heat transfer to ambient. And what that means now for the heat losses, I can show you here. So you see here the heat loss flow is function of the insulation thickness. That with that the slope of this curve decreases dramatically with very high insulation thicknesses. And that's why it doesn't make sense to just apply a high amount of any, let's say, lousy insulation material around your process, but rather search for preferably efficient ones. So now I show you the thermal insulation techniques I mainly considered for my research. First, on the left side, this is infrared radiation shield insulation, or IRS, consisting of many metal sheets that should reflect infrared radiation and that are kept in distance by some spacers and that are fixed with screws. And on the right side, you see some porous thermal insulation materials that are investigated. Those are stable for high and ultra-high temperatures. That could be graphite fiber mat, microporous fumed silica board, and alumina fiber mat. And now I show you the working principle of these techniques, and I start with how they mitigate thermal radiation. So on the left side for the IRS, when there's an incoming infrared radiation, a preferably high amount of that radiation gets reflected, the rest is absorbed by the first sheet and then re-emitted to the other sheet where the same mechanisms are going on. So the more sheets you have, the more effective is your IRS thermal insulation. For porous thermal insulation materials, there's mainly infrared radiation scattering going on. So that means every part of the solid structure of this porous material scatters infrared radiation dependent on its optical properties and also a little on the size or on the dimensions of the structure. And now I show you the other heat transfer mechanisms going on in thermal insulations for IRS besides thermal radiation, solid conduction via the spacers, and gas conduction and convection in between the sheets is going on. The characteristic material parameter for IRS is the emissivity of the sheets. For porous thermal insulation materials, besides thermal radiation, we have solid conduction and gas conduction, so solid conduction via the solid structure and gas conduction inside the pores going on. Usually, convection is not taking place there as the pore size is too small and thus the flow resistance is too high to establish a convection flow. The characteristic material parameter for porous thermal insulation materials is the effective thermal conductivity. And why it's effective, it's called that because it's not only containing one conduction mechanisms, but others, and also including thermal radiation. Now I come to the market screening for porous thermal insulation materials. And the main criteria for that screening were permanent temperature stability, what we want to have as high as possible, then costs and effective thermal conductivity, which we both want to have as low as possible. And here you already see the results for the most promising insulation materials I found in my research. So you see here the thermal conductivity is a function of the temperature measured in air or nitrogen atmosphere at atmospheric pressure. And what you see here is all manufacturer data. And the most promising insulation materials I found by the criteria named before, or at least by two of those criteria, were zirconia fiber boards, graphite fiber mat, alumina fiber board and fiber mats, and fumed silica board. And on the right side you also see some prices. I know it's always difficult to present some prices as they can differ a lot, as you know, dependent on the amount you are asking for, the region you are in, and so on and so on. So this is prices for comparable low amount of this insulation material, like an amount for our Amadeus prototype. And what you can also see in this graph is the maximum temperature of each insulation material as these regression lines, and on the right side at the respective maximum temperature of the material. So, and up to its maximum temperature of 1000 degrees C, the fumed silica board has the by far lowest thermal conductivity, and it also has the lowest price in this line up here. And from temperature from 1000 to 1800 degrees C, the zirconia fiber board 2 offers the lowest thermal conductivity, but also has a very high price. And from 1800 to 2000 degrees C, the zirconia fiberboard 1 in this lineup offers the lowest thermal conductivity, but has an even higher price. Because of these very high prices, it very much makes sense to look at the materials between, so the graphite fiber mats and the alumina fiber mats and fiber boards. And as we also want to look at, as I told you, the most cost-efficient material. So how can we make now the best choice for our material by means of cost efficiency? We need to rate this cost efficiency by any means. So I rated this in a first simple step with a conductivity cost product, which I call CCP, and which by the name is obviously the product of the thermal conductivity of the insulation material and the specific costs. And as we want both values to be as small as possible, we also want the CCP as small as possible. So the lower the CCP, the higher our cost efficiency. And as you saw on the slide before, the thermal conductivities are dependent on the temperature. If we compare materials with each other, we have to do this at the same temperature. So I did this for 1400 degrees C for zirconia fiberboard 2 and graphite fiber mat 1. The one has the lower thermal conductivity and the higher price, the other the higher thermal conductivity and lower price. And what you can see here, that we get a 10 times higher value for the zirconia fiberboard 2 than for the graphite fiber mat, which means we could say graphite fiber mat is 10 times more cost efficient than the zirconia fiberboard. This simple calculation is only valid or significant for a flat wall, though, because this high heat transfer surface with high insulation thickness is not considered herewith. To consider this, you should carry out some thermal simulations for your indicated application. And there you can then vary your insulation material, your insulation material thickness, and then evaluate the heat losses and cost and make maybe a heat loss cost product which you can rate your cost efficiency with. Another good idea is, as we also heard in the session before, is the combination of different thermal insulation materials, especially when you have material like fumed silica board, which has very high cost efficiency, but on the other hand, a lower temperature stability than your maximum application temperature. That's why you cannot put it everywhere. But then you can put this material outside, and on the inside, only where the temperature is that high, you can put this high temperature stable insulation material with a little lower cost efficiency. And so with this you can reach a lower volume and cost for your insulation. And for this approach, it's absolutely necessary to run some simulations and better some tests to not exceed the maximum temperature of your outer insulation material. So I did this here. What you can see here is a picture of a simplified model of one of the first drafts of our Amadeus prototype. And here I did some simulations where graphite fiber materials are in the middle and fumed silica board is outside. Now we use, for the case, because of the simplicity, we only use graphite fiber materials for our prototype. Now I come to the market screening for infrared radiation shield materials. And the main criteria for the research are very similar to those of Perrault's thermal insulation materials. It's we want a preferably high permanent temperature stability and preferably low cost, and in this case, emissivities. And here you already see some of the results of this screening. So IRS materials you could use at ultra-high temperatures could be molybdenum, tungsten, tantalum, or graphite. And here you see the total hemispherical emissivities for different temperatures. And as you can see, for these three metals, the emissivity rises with rising temperature, which is a behavior which we don't want, because the higher the temperature, the higher is the share of radiative heat transfer on our total heat transfer. But for this temperature, unfortunately, the emissivity gets higher, so the effectiveness is getting down of our IRS. This is the other way around for the graphite, as you can see here, but still at 1500 degrees C you have much higher emissivity than for the metals. And as you can also see here, these metals have more or less the same emissivity. And now, as we want to rate always the cost efficiency, we also want to have a look at some prices. So I asked these manufacturers for prices for these materials, and I got offered these prices for these thicknesses of foils or sheets, and these prices are in euros per cubic meter. So you see, out of the three metals here on top, the molybdenum has the lowest price with 700 to 900 euros per cubic meter. Tantalum has a quite high price, and graphite has an even lower price, but also, as you saw before, quite high emissivity. And molybdenum has also a lower temperature stability. That's what IRS manufacturers suggest as a maximum temperature in vacuum for the purpose of IRS. So now it's again a question of cost efficiency, what material to use, if it's better graphite or molybdenum. And in the end, I chose molybdenum for the cost efficiency comparison of IRS and Perrault thermal insulation materials, what I present you right now. And this is how this comparison works. I compared the heat flux density through an IRS made of 10 sheets with the heat flux density through a thermal insulation material, Perrault thermal insulation material, with the same thickness and with the same boundary temperatures. So first, some general conditions of this comparison. I calculated the heat transfer through a flat wall, and the temperatures, the boundary temperatures, were 1,500 degrees C on the hot side and 1,000 degrees at the cold side. I chose these temperatures because, as you saw before, you shouldn't use the molybdenum for much higher temperatures than 1,500 degrees C. And for lower temperatures than 1,000 degrees C, we already have the fumed silica board with a quite high cost efficiency. And as mentioned before, the thickness for this comparison should be the same for both techniques. And for the material cost evaluations, for the cost evaluation, only material costs are considered, so no construction cost here. So now some more technique-specific boundary conditions on the left side for the IRS. I told you already that I used unoxidized molybdenum with a price of 900 euros per square meter and a total hemispherical emissivity at the mean temperature between the boundary temperatures of 1,250 degrees C of 0.175. I assumed in here a perfect vacuum and no spacers in between the sheets, so no gas heat transfer, no solid heat transfer, only radiative heat transfer. And I did this because this was a first rough shot just to see if IRS can compete by means of cost efficiency with Perrault's insulation materials at all. The sheet thickness, I took 1.3 millimeters, and the sheet distance was varied during this investigation. For Perrault thermal insulation materials, as competitive material, I chose the graphite fiber mat with cost of 17 kilo euros per cubic meter and an effective thermal conductivity at the mean temperature of 0.23 watts per meter Kelvin in nitrogenous atmosphere gas. And you can already see here that these are conditions very much in favor of the IRS, where I assume perfect vacuum, where here I assume nitrogen atmosphere. The thickness will be varied within the thickness of the distance of the sheets of the IRS. Here are the equations, how I calculated the heat flux densities for both cases. I don't want to tire you too much with the explanation of these equations. I just want to point your attention on one thing, and that is that the heat flux density through the IRS, or the radiative part of the IRS, is not dependent on any thickness or sheet distance, as in a perfect vacuum for radiation the distance just doesn't matter, but it's dependent on the number of sheets here. Whereas for the Perrault thermal insulation materials, the thickness does matter, and it's a significant role in the heat flux density, of course. Now I also wanted to rate the cost efficiency of both techniques, and in this case I calculated an area-specific heat flux density cost product, which I call here HCP, in kiloeuros times watt per square meter. And so, yeah, it's the same. The name says again, it's the product of the heat flux density and area-specific cost of these materials. And again, the lower this HCP, the higher is the cost efficiency. And here we come to the results for a distance between the IRS sheets of 10 millimeters. And this thickness is actually the lowest thickness you should have for this kind of IRS construction. That's what the manufacturer told me, just to prevent the sheets from touching each other due to non-uniform temperature expansion. And with this 10 millimeter distance between the sheets, we get a total thickness of 9.3 centimeters, which we then apply to the graphite fiber mat in nitrogen. So here in this graph, you see in red bar the heat flux density, and in blue the specific costs. And you can already see that for graphite fiber mat, we have lower values than for the IRS and vacuum. So we can already see here that the cost efficiency will be higher for the graphite fiber mat. But what if we do reduce the distance between the IRS sheets to 5 millimeters, even though manufacturers might say it's not a good idea? Then you see that the heat flux density, okay, for the IRS nothing changes as the number of sheets is the same and distance doesn't matter. But for the graphite fiber mat, the heat flux density rises and is here in this case even a little higher than for the IRS and vacuum. But on the other hand, also the costs go down because you have less material here. And the product of these two values is in both cases the same. So you can compare the HCP now for both. And you see here, if we do the calculation that for the IRS, the heat flux density cost product is 10 times higher again than for the graphite fiber mat. So you can say that the graphite fiber mat is, in this example, has a 10 times higher cost efficiency than IRS. So when looking at that, or by the means of cost efficiency, I would suggest going for Perrault thermal insulation materials rather than this construction method of infrared radiation shields. But if you have some spaces where you don't want any fiber contamination, then this infrared radiation shield still is a very good idea. So now I show you some optimization potential for the efficiency of thermal insulations. And I want to concentrate on 2 points. First point is the atmosphere gas for thermal insulations. Second point is the construction of the IRS. And I want to start to show you the potential of a vacuum atmosphere for open porous thermal insulations. In this graph, you see the share of total heat transfer of infrared radiation, gas conduction, and solid conduction for a random porous insulation material as function of the temperature. So you see that for low temperatures, gas conduction has by far the biggest share of the total heat transfer. But with rising temperatures, infrared radiation gains bigger and bigger shares. So until an ultra-high temperatures, it has the dominant or the highest share of the total heat transfer. Solid conduction, on the other hand, is quite low for nearly every porous insulation material you might find. What you can see here, even though radiation is dominant at high and ultra-high temperatures, gas conduction still has a significant share of the total heat transfer. And you can decrease the share or maybe totally get rid of it, depending on the vacuum pressure, if you apply a vacuum in your insulation space. So here I bring you 2 examples for effective thermal conductivities in air or nitrogen and vacuum atmosphere. On the left side for the alumina fiber mat 1, on the right side for the graphite fiber mat. The lower curve is in both graphs for the vacuum effective thermal conductivity, and you see that you can in both cases decrease the thermal conductivity significantly by applying a vacuum. But if for any reason a vacuum isn't applicable inside your insulation space, but you probably need an inert gas anyways, then it makes sense to look at the choice of your inert gas, because they have different thermal conductivities. So here you see the thermal conductivities as function of the temperature for nitrogen, argon, krypton, and xenon. And you see that you can have much lower thermal conductivities than nitrogen and lower than for argon if you use krypton or xenon. But on the right side, you see, again, the prices of these inert gases. And you might think that xenon is probably not feasible for most of the application we're talking about, unless you go to space, of course, and everything is possible. But as you maybe remember, the very high prices for the ultra-high temperature thermal insulation materials, even krypton could be a good idea by means of cost efficiency for your application, and maybe better than argon or nitrogen, which is for some applications not even applicable because of reactivity. Okay, now an idea to optimize the construction of IRS. And I'm thinking about an ultra-high temperature multifoil insulation. So every one of you might have seen this golden foil wrapped around some spacecraft object like this Mars Reconnaissance Orbiter here. And this foil actually consists of many foils, as you can see here on the left side, kept in distance by some textile mesh spacer material. The advantage of this construction compared to the rigid construction I showed you before is you need less thinner IRS sheets, so you have less materials costs, and you can have much smaller distances between the sheets. So you have less space requirement for even more IRS sheets, and thus a higher volume-related efficiency. This particular material here isn't stable for ultra-high temperatures, though, as it consists of polymer foils coated with silver or gold. But there are also materials available for ultra-high temperatures, which you can see here. So multifoil for up to 1,450 degrees C has been already used for the atmosphere, for the heat shields, for the atmosphere re-entry of spacecraft objects. And on the left side, you see one example of one of these materials. And this consists, in this example, the foils are out of flexible alumina sheets coated with gold, which makes it stable up to 1,000 degrees C, and this is the case in this example. Or you can coat it also with platinum, which makes it stable up to 1,450 degrees C. As bases, you see here low-density alumina fiber mats, and the effective thermal conductivity of this particular material you can see on the left side, and I compared it here with the thermal conductivity of fumed silica board. And the upper curves are for atmospheric pressure, and the lower curves for a vacuum pressure, or for vacuum. In this case for foils. And you see that for atmosphere pressure, fumed silica board has still a lower thermal conductivity, and for high vacuum, at least for higher temperatures. And also the costs are much higher compared to the fumed silica board, with around 100 kilo-euros per cubic meter compared to the 2.5 kilo-euros per cubic meter. But this is only the values for this particular material. So the effective thermal conductivity and cost, I think, could be decreased by, for example, thinner spacers and other foil materials like molybdenum or maybe graphite with a high amount of foils. And such materials also already exist. Okay, so let me just sum up what I talked about the last, I hope, half an hour. We saw that Perrault's thermal insulation materials for temperatures up to higher than 1,000 degrees C have significantly higher prices in thermal conductivities than for lower temperatures. And I told you that the combination of insulation materials, and we saw in the session before, can save space and cost both. Then I showed you that Perrault's thermal insulation materials have significantly higher cost efficiency than the IRS construction I showed you at ultra-high temperatures. And we saw that vacuum or low lambda, so low thermal conductivity inert gases, can reduce the heat transfer through your thermal insulation. In the end, we saw that an ultra-high temperature multifoil insulation could be a promising thermal insulation for ultra-high temperature thermal energy stores. And now, as the last slide, I want to show you some further research I did for ultra-high temperature thermal energy stores. Just an example here. I classified, or I found a way, I proposed a way to classify the energy losses of ultra-high temperature thermal energy stores. So there are already standards available for the classification of heat losses of hot water stores, and I applied those, or I adapted those for ultra-high temperatures. So here's an example for the energy label. The Europeans in the audience probably know this label from your refrigerator or washing machine, and this is now also available for hot water stores. And here you see some results. So I did some simulations. I varied the PCM volume and the maximum temperature, and I got these results here, just as an example. So if you're interested in this study or in this classification method, please don't hesitate to contact me after my talk. So in the end, I want to thank the European Union for the fundings of our Amadeus project and you for your attention. Thank you.
Thank you, Stephan, for your very illustrating talk. Now it's time for questions. Anyone want to ask anything? Okay. Alejandro?
Yeah, I know we talked about this like 2 years ago, but at that time we were talking about using ceramics as these IRS systems instead of metals. Could you tell something about the possibility of using ceramic as infrared seal reflectors?
Yes. As you saw, also these are ceramic foils, flexible ceramic foils, so aluminum foils. Yeah, but the emissivity is, of course, not as low as if you coat this with metals like this. But you could use it without the metal, and you need more foils, as I also suggested for graphite. But yeah, the emissivity is a bit higher. That's a drawback, and it's difficult to compose this in a way that are not too fragile. This is also, as you can see here, there's also some cracks going on. So I think it's better to use a pure metal or a metal alloy with low corrosive materials.
And also, could you comment something on the last slide on why you get better classification for a small volume?
Yeah, that's that's a good question, and it's really it's because of the calculation method of this for these energy labels. So in the standard, they say, okay, they rate the heat losses, or you rate the heat loss, and the heat losses as a function of the volume, and the way they rate it to get an A+ or an F is in a way that is not advantageous for a higher volume. So this will be the case as well for your hot water store. So maybe for political reason, I don't know why they rate it like that, but there's nothing to do with the thermal properties and with the heat losses, because actually the higher your volume, the better it is. So the higher the surface to volume ratio, the lower your heat losses should be, dependent on the energy stored or the volume.
So, would you propose to use this classification system for ultra-high temperatures, or to change completely to another?
Yeah, I would propose to change this. There's also another classification method, the standard EN 12977. This also, you can rate this also with this standard, and there they managed it that you have this more or less the same value if you increase the size of your storage. In this case, they didn't manage to do it. I don't know why, but I would suggest to change this classification, even for hot water stores and more for ultra-high temperature thermal energy stores, because I don't know why it's of advantage to have a smaller store.
Any other question? Well, if not, we thank Stephan again.